In this lecture, we are going to introduce the concept of osmosis. Osmosis, like freezing point depression and boiling point elevation, is a colligative property. So, it does not depend on the identity of the solute, but the concentration of the solute. Look at this setup in the PowerPoint slide. It has two chambers separated by a semi-permeable membrane. On the left hand side of this setup is a chamber with pure solvent. On the right hand side is a chamber with a solution. Now, if this membrane is permeable only to solvent, let's assume that the solvent is water, then solvent will flow from the left hand side to the right hand side because the chemical potential of the pure solvent is higher than the chemical potential of the solvent in this solution. To prevent water from flowing from the left to the right, we can apply a slightly higher pressure on this piston on the right hand side. So, on the left hand side, the piston has a pressure P. On the right hand side now, the piston has a pressure P plus pi. This pi is called the osmotic pressure. So, this is the amount of pressure that must be exerted on this compartment to prevent flow of water from the left hand side to the right hand side because of the gradient in chemical potential of the solvent. We will now try to derive the Van't Hoff equation, which relates the osmotic pressure to the concentration of the solute. Remember, this is the molality of the solute, so it has no information about the identity of the solute. And this is given by justification 3.9 in the book. Now, if I am applying a higher pressure on the right compartment and the lower pressure on the left compartment, and the osmotic pressure is just right to prevent flow of solvent from left hand side to the right hand side, then this system is at equilibrium. If it is at equilibrium, then the chemical potential of the pure solvent on the left hand side, which is at pressure P, must be equal to the chemical potential of the solvent in the mixture, which is at pressure P plus pi, which is the osmotic pressure. Note that I do not use the star sign here because now this is not the chemical potential of pure solvent. Yes? So, let us try to expand this term a little bit. On the right hand side, the chemical potential of the solvent at a pressure P plus pi is given by the chemical potential of the pure solvent at the same pressure plus RT multiplied by the logarithm of the mole fraction of the solvent. If you look at this term now, the chemical potential of the solvent at a pressure P plus pi will be given by the chemical potential of the solvent at a different pressure plus an integration over the molar volume multiplied by dP, and this is going from pressure P to pressure P plus pi. This equation comes from here. Yes, if the temperature is constant, this term falls off. So, dG equals V dP, and if we make it molar on both sides, then it becomes molar, and therefore G, and if you integrate it between two different pressures, then G at a final pressure minus G at an initial pressure will be equal to integral of the molar volume multiplied by dP from the initial pressure to the final pressure. And the molar Gibbs energy is nothing but the chemical potential. Okay. Now, for liquids, the molar volume is fairly independent of pressure. So, I can write this, I can bring the molar volume out of the integral, and then we have P plus pi minus P, P cancels out, and this becomes the chemical potential of pure solvent at a pressure P plus the molar volume multiplied by the osmotic pressure. Now, I can substitute this term into this equation, and then I can get that the chemical potential of the solvent in the solution is equal to, at pressure P plus pi, is equal to the chemical potential of the pure solvent at pressure P plus this product, molar volume multiplied by the osmotic pressure, plus RT log of XA. Yes. And now we are going to use some nice mathematical tricks. So these two terms remain the same, but I can write the last term as log of 1 minus XB, because the sum of the mole fractions of the solvent and the solute must be equal to 1. Now it turns out that if XB is fairly small, this can be written as minus XB, log of minus XB. I'm sorry, that is not correct. There is no log here now. So if XB is very small, then it can be shown that log of 1 minus XB will be approximately equal to minus XB. Okay. So let's rewrite this once again. So now you have the chemical potential of the solvent at pressure P plus pi equals, let me write this again here, the chemical potential of the pure solvent at a pressure P plus the molar volume of the solvent multiplied by the osmotic pressure plus RT multiplied by minus XB. Now if I take this whole thing and I substitute it on top here, then I can write this as and now I can take the minus sign out, minus RT XB. Yes. Remember this needs the approximation that the mole fraction of XB of X of the solute is very small. So it's a dilute solution. And now this term cancels out. And then I simply rearrange terms here, and we start to get what is looking very much like the ideal gas equation. Let's approximate this a little bit further. Now XB is given by the number of moles of B divided by the total number of moles. Now here the number of moles of A is much higher than the number of moles of B. Yes. So for example, you have 10,000 moles of A and maybe you have 10 moles of B. Yes. So then the denominator here can be approximated as NA, because 10,010 is almost as good as 10,000. Now NA multiplied by the molar volume of A is simply equal to the total volume of the solution. So this becomes RT multiplied by the number of moles of B divided by the total volume of the solution. And this is the Van 't Hoff equation. Now the Van 't Hoff equation relates the osmotic pressure of the solution to the concentration of the solute, and it assumes that the solution is dilute with respect to the solute. What is remarkable is you get an equation very similar to the ideal gas equation. Yes.